Ladies and gentlemen, hello and welcome once again. Coming to you not quite live from One Take Studios, where today's topic is everybody's favorite, complex numbers and roots. Some of you are asking, aren't all numbers complex? Well, actually, technically, yes. However, we're going to add a fun new twist to this. Everybody's favorite, imaginary numbers. Imaginary numbers. Now, unlike the Easter Bunny, imaginary numbers actually have a structure to them. They have a rule. All imaginary numbers are based on one fact. By definition, I wrote it in cursive, a little bit easier to see it in cursive. Oftentimes textbooks will use it in italics, I, is equal to the square root of -1. I is equal to the square root of -1. So based on that one fact, that is the foundation of every single imaginary number on the planet. What does this mean? This means that math problems that you thought were impossible are now possible. I know, it's exciting. Now you can do even more math. So things that you used to say couldn't be done. For example, the square root of -100. No, it can't be done, because square root means I take a number times itself, and a positive times a positive is a positive, and a negative times a negative is a positive, and I can't do this. Or can you? Separate the -1 from the 100. That's legal. -1 times 100 is -100. What's this? There's my imaginary part. There's my I. What is the square root of 100? The square root of 100 is 10. This is 10i. Don't make it more complicated than it is. Complicated things will come. This is not one of them. So we are simply simplifying. Right now, let's look at another one. I'm going to go, let's see, the square root of -32. Again, I want to view this in different pieces. I'm actually thinking, all right, so 100 actually was a perfect square. That worked out pretty nicely. 32 is not a perfect square. So what factor of 32 actually is a perfect square? I know there's a lot of people out there that break these things down using factor trees and stuff, which is lovely. However, most people then don't know what they're doing. They just make factor trees and circle stuff, and yeah. Think. If I'm simplifying a square root, my rule is I can't leave any perfect squares under a square root. Which means 16 is a perfect square and a factor of 32. In fact, it is 16 times 2 that makes 32. This piece is a perfect square. This piece is not. I don't want to forget the negative, so there's my -1 as well. If I multiply all these back together, I get the square root of -32. What does this mean for my simplifying? Here's your words of wisdom for the day. Are you ready? Do what you can do, and do not do what you cannot do. I can take the square root of 16. That's 4. I can take the square root of -1. As of today, that's going to be I. I cannot take the square root of 2, therefore I will not take the square root of 2. That is simplified. That's it, right there. Ta-da! So do what you can do, and do not do what you cannot do. Notice where I placed I in both of these cases. I put it after the 10 and after the 4. We place I a lot like we would place a variable, like x. So technically it's not a variable, but it behaves an awful lot like a variable in many occasions. Yeah, I know. I would like to jump to some equation stuff here as well. So let's say, as a different type of example, I have x squared equals -36. All right, so this was just simplifying, boom, simplifying, boom. This is an actual equation. I'm solving for x. How do I get the x by itself? I call these isolation problems. In fact, I'm going to write that word over here. Isolation. I don't think I've seen any textbook use that term, but isolation to me means it's quadratic, yes, but there's only one x in the problem, and it's x squared. No other x's anywhere in the problem. If I can isolate the x squared, if I can get it by itself, I just have to take the square root. So I'm taking the square root of x squared, and I'm taking the square root of -36. The square root of x squared Inverse operations undo each other. There's my x by itself. And the square root of 36, as of what we now know, the square root of 36 is 6, and the square root of a negative is I. Did you notice? I left a space right there. How many answers does a quadratic have? Because the vast majority of people are already on to the next problem and their brains aren't really thinking. Quadratics always have 2 answers. Technically, positive 6i will work, but so will negative. Oftentimes, if I say take the square root of 36, you would just tell me 6. But if we are solving equations, you've got to think plus or minus, because quadratics always have 2 answers, plus or minus, right there. There we go. So if I'm solving a quadratic and I finish and I don't have 2 answers, I didn't do something correctly. Plus or minus 6i. This is my solution. I can do something close to that. Let's try one more of these guys. X squared plus 48 equals 0. Again, in my mind, this still fits the isolation model because I have only one x. And if I can isolate that x and get it by itself, I can take the square root. So that's going to be x squared. If I subtract the 48 equals negative 48. Convenient. It's negative again. Which means I want to take the square root of the x squared, and I want to take the square root of the negative 48. There's my x. What is in 48? Now think about this in pieces parts for a second here. I know I've got the negative 1. I'm going to kind of squish this here. 48, has a factor of 16 in it, and 3. Double checking myself. Yeah, that's good. That's good. Alright, so again, kind of like what I was doing up here, you do what you can do, and you do not do what you cannot do. Alright, I can take the square root of 16, that's 4. I can take the square root of negative 1, that's I. I cannot take the square root of 3, so I will not take the square root of 3. Did you remember this time? Did you? Again, it's quadratic, it has 2 answers, so when we have the square root, we need to think plus and minus, plus and minus. Now there's a general rule of thumb, because some of you are like, yeah, but you didn't do plus or minus up here. Here's the difference. In both of these problems, in the original problem, there was no radical sign, there was no square root. In the process of solving, I had to put in the square root sign. Consequently, plus or minus. These 2 problems right here both started with square root signs. When your problem starts with a square root sign, you simply give the positive answer. Positive answer. Putting the sign in yourself, plus or minus, plus or minus. Alright, so you need a gigantic note to self about this plus or minus thing because you are going to forget. It's going to happen. Rawr, don't forget, okay? Alright, so this is our overall intro here to imaginary numbers, and I want to look at a couple little things here that go with this. Alright. Can I leave this here? I can leave this here for now. All right. So, complex numbers. Dun-dun-dun-dun. Fit the form. A plus bi. So this is our standard form for complex numbers. If you remember, we have standard forms for quite a few things, polynomials, and they always start with a and they go from there. So a plus bi. The a part does not have an I. Therefore, it is blind. No. It is the real part because it doesn't have the imaginary piece to it. And this piece here, the bi, does have the I. This is the imaginary part. Imaginary. Cool. Alright. So let me ask you this then. If I've got something in this form, what happens if b equals 0? 0 times anything is... gone, right? Poof. Leaving me with just the real part. So if b equals 0, I simply have a real number. Real number. I am trusting you, by the way. That's a number symbol. It's not a hashtag. So complex number is a real number. Dealing with that. Kind of rough. All right. What if a equals 0? If a equals 0, then this piece is gone, and I'm left with just the bi, which is just the imaginary part, otherwise known as pure imaginary. Can I squeeze it? I can. There we go. All right, so if A is 0, I have a pure imaginary number, and if B is 0, I simply have a real number, which means that all of these real numbers that you've been working with since, I don't know, kindergarten, have all been complex numbers. It's just that the B value was 0, so the imaginary part was not around. See, you've been doing this forever. You got this. Okay, so that's our standard form. I would like to remind you about the quadratic formula, because these were lovely isolation problems, but not everything can be isolated. Not everything has the single x squared by itself type of thing, and sometimes we've got things that are more interesting. Ladies and gentlemen, I do not often recommend that you memorize things in math, because a lot of math should simply make sense, and if you're memorizing things, chances are they don't actually make sense. This is one of those few things, however, though, that you're simply going to need. And this is me decorating it for you, making it very, very pretty as you write it down. So x equals, I can sing it to you if you want. Song sometimes helps you remember things. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. There, if that helps, great. If it doesn't, the song was for free, and you're welcome. Alright, the only thing I don't like about that song is they call this negative b, and I really don't like that. This is the opposite of b. Because you don't know what b is, this may end up being a positive or a negative value. But that's going to be the opposite of b. Alright, so what happens now? What happens if, oh goodness gracious, there we go. I can't use isolation. What happens if I've got this instead? So I'm going to go with f of x is equal to x squared, and we're going to go minus 2x plus 5. Okay, all right. I'm going to ask us to find the zeros. Finding the zeros is just a fancy way of saying, make this equal to 0. What values will make this equal to 0? So this is just a fancy way of writing an equation of 0 equals x squared minus 2x plus 5. This is standard form for our polynomial. If you don't have it equal to 0, you cannot use quadratic formula. So set it equal to 0 first, and then you can use quadratic formula. And we can see the pieces parts here, hopefully. In front of the x is a 1, which is our a. In front of the b, in front of the x squared is a 1. In front of the x is a negative 2, which is our b. And this is our constant by itself. It is c. Again, stemming from, I'm going to throw this over here, standard form f of x equals ax squared plus bx plus c. And again, this thing has to be set equal to 0 in order for this to work. Otherwise, you are out of luck and you're doing weird things that will ultimately be fruitless. All right. Well, see, here we go. We've worked with these before, and we've worked with solving them by factoring. The problem is, there's nothing that I can multiply that's going to make 5 that ultimately is going to add to make negative 2. So factoring is off the table for this. And believe it or not, if I graph this thing, all right, tiny little inaccurate sketch, but this is what we got going on here, guys. Don't know exactly where this thing is going to be placed, but I do know that if I graph it, it's going to be up here someplace. I know that my vertex is going to be above the x-axis someplace, and I know that it's opening upward. Why does this matter? Because sometimes we find the zeros by finding the x-intercepts. When will this little thing cross the x-axis? Never. So I can't factor, and the graph is not going to help, and I can't use isolation because isolation said I have the x squared and no other x's. I have one x in the problem. I clearly have two x's in this problem. I have an x squared and an x, so this is not even an option. I have to go here. I can do this. X is equal to the opposite of b, negative 2, positive 2, plus or minus the square root of b squared. People mess this up. Watch what I'm doing. I just put this in parentheses because my b is negative 2 and I'm squaring a negative 2. This number had better always be positive, otherwise you've just messed up. This is a square. It's going to be positive. I promise you it will never be negative. Minus 4 times a, which is 1 we said, times c, which is 5. I've been doing this for 22 years. Do I still write all this out for myself? Yes, yes I do. Over 2a, so that's 2 times 1. There we go. Simplify, simplify, simplify. 2 plus or minus. What the heck am I going to have under my radical here? Let's do this slight slow-mo. Negative 2 squared is 4. Minus 4 times 5 times 1, that's going to be 20. And that's all over 2. And it bothers me that that's too long. Shorten, shorten, shorten. There we go. That's better. All right, so continue simplifying. This, by the way, is just order of operations. If you get this wrong, it's because you made an order of operations mistake, most likely. Or maybe you made a calculation error. Over 2. Square root of 16. Before we would have said that there is no real answer. And quite frankly, that is true. There is no real answer. But we have imaginary numbers now, and we can take the square root of negative 16. So this is now x is equal to 2 plus or minus, all right, the square root of 16 is 4, the square root of negative is I, this is going to be 4i over 2. And I have 2 terms on top. That's what I call things that are added and subtracted, 2 terms, and they can both be divided by 2, so I'm going to divide them both by 2. So x equals 2 divided by 2 is 1 plus or minus 4 divided by 2 is 2i. Ladies and gentlemen, that is the answer, which happens to be, by the way, in standard form for a complex number, to this equation. The plus or minus is built in, so you don't have to worry about forgetting it. So that's actually kind of a nice benefit. But again, you see, every time we work with the quadratic, there are 2 answers. Sometimes they're 2 real answers, sometimes they're 2 imaginary answers, and there are other things that could happen in life. By the way, you will never get one of each. You will never get one real and one imaginary answer for your quadratic because of the plus or minus. All right, so we are talking about these imaginary numbers. They were on the ark with Noah. They travel in pairs. There's always 2 of them. Plus or minus is everything. These are what we would consider to be complex conjugates. So the 2 answers here are 1 plus 2i and 1 minus 2i. Some people would call them opposites. That's not true. That's a plus, that's a minus. Those are opposites, but this is a positive 1 at the beginning of both. So these are not true opposites. These are complex conjugates. So if you ever have one imaginary answer, you automatically have 2. If you happen to know that one of your imaginary numbers is 2i, then the other one's going to be negative 2i. If you happen to know that one answer is 12 minus 72i, well, then its complex conjugate is going to be 12 plus 72i. All right? The plus or minus goes with the imaginary part of things. They always travel in pairs. You can't have one. All right? So don't let this scare you. Be careful. Pay attention to details. All right? Know the difference between these 2 types of problems, x squared and x versus just plain old x squared and no other x's in the problem, because once people see this, their brains have a hard time going back here, and these are actually easier usually. All right? So this is an option. Keep that in mind, and you may need to practice simplifying your radicals for working with these as well. All right? Thanks, guys. Have fun.